Okay, so we're going to look at now ring opening of epoxide, section 14.10. This is lesson 5. It turns out now we are going to reap what we have been sowing. We have been working very hard to consider shape and polarity, the two predominant factors that help us predict where the electrons are and what they're going to do. So if you understand SN1, SN2 reactions, deeply understand SN1, SN2, and if you deeply understand shapes, that is tetrahedra and trigonal planes, then this is going to look easy for you. Does that make sense? Let me say it again. SN1, SN2, tetrahedra, trigonal planes. This matters very much. This is going to be easy for you, okay? Nucleophile, right? And electrophile, which I haven't used as an E yet. We'll do that later this semester. Nucleophile and substrate, right? These terms, if they mean something to you, if you understand them deeply, this video is going to be easy. All right. So, because of their significant ring strain, epoxides, where's my pen? Because of their significant ring strain, epoxides have great synthetic utility as intermediates. In other words, they're very reactive. And we can make a lot of things with them, okay? So propose some reagents that might react with an epoxide to form a specific functional group. Now, I would like you to, and you ought to do this, you ought to go back and say to yourself, if I'm going to have some reaction, I didn't leave myself enough room, did I? Plus something gives me something else. Okay? If I'm going to have some reaction that looks like this, what might this be? And what might this be? Okay? In other words, think of it in SN1, SN2 parlance. Okay? Now, we're going to be doing that over the next couple slides, but if you could pause the video right now and think about that. If I have ring strain there, what might a nucleophile be? What might a leaving group be? Okay? Where are the positive centers and where are the negative centers? So this is something that I've brought up a couple times. I know I'm investing a couple extra minutes here at the beginning of this slide. But what I've said is the primary question in organic chemistry is what are the electrons going to do? Okay? So what we have to do is we've got to find where the greatest density of electrons are and where the most vulnerable positive center is. And that is going to attack that. And that's it. That's what we're doing here. Okay? Pause the video and think about that. Probably already did. Okay, so let's move on. Strong nucleophiles react readily with epoxides. How? Why? Of course. Look it. This was a polar bond already, right? Remember that symbol from Principles 2? This is a polar bond. And if that's a polar bond, we have not only a partial positive here, but because of the ring strain, it's open. It's really easy to get to. Okay? So shape and polarity. Those are my two things, shape and polarity. So my nucleophile comes, boom, and hits that, and wham, this guy leaves. Now, what's the leaving group? The leaving group is an alkoxide. Right? That's the leaving group right there. Normally we wouldn't see an alkoxide leave. I think that's what this says. Just a second here. Yeah. The resulting alkoxide is then protonated, but we normally wouldn't see that. But why does it leave here? That's why it leaves. Okay? So, look at this. In general, I just said that. Alkoxides are not good leaving groups. They're not good leaving groups. But the ring strain associated with the epoxide increases its potential energy. In other words, it's already too high in energy. And so it makes it more reactive. So let's look at this energy diagram. So if an ether here, that's what an ether looks like, and an epoxide looks kind of the same, right? You see the similarity there? Okay. Except these ethers go off other places, okay? So since this has got ring strain, it's ratcheted all the way up here. Its potential energy is up here. It's reactive. And because its energy is high, and also because of the ring tightening out here, the other atoms, which are as shown here, would just be hydrogens, right? But they're stretched out. That makes it very vulnerable to attack. Okay. See, the epoxide reaction is both kinetically and thermodynamically favored. Why? All right. These are such important terms. Gosh, I really would, if I could force you to pause the video and think about that, look them up, then you'd be better off. If I could force you to do that, you'd be better off. Consider doing it. Kinetically and thermodynamically. Okay, let me suppose that those of you who had the spirit to do it did it. Thermodynamically, right, that's an energy term, and you can see now that, where's it? Where's my marker here? Thermodynamically, right, from there to there, right, delta E is negative, right? But from here, delta E is positive. How do you spell greater than, right? That means it's uphill. Right, so that would mean this is endergonic or endothermic. I didn't say anything about the entropy. I haven't even thought about it. So let me just use endothermic, okay? That's endothermic, but this is exothermic. So thermodynamically, the epoxide is favored, right? Because this is exothermic, okay? Now, what about kinetically? Why is this faster? Aha, this is faster because the activation energy is small compared to this activation energy, right? Whoops, whoa, uh-oh. Go back. Compared to this activation energy, right? So this is going to be faster. Don't lose these terms, kinetic and thermodynamic. They help us. All right, they're tedious terms right now, but the more you use them, the more helpful they become. Okay, so the ring opening of epoxides is both kinetically favored and thermodynamically favored over the reaction with an ether, and this is the reason why. Okay. Now, epoxides could have many different kinds of nucleophiles. I'm going to ask you to pause the video and say, what is the nucleophile for each of these? What is the nucleophile for each of these? Pause the video. Okay, so the nucleophile for this guy is an alkoxide. The nucleophile for this guy is cyanide. The nucleophile for this guy is thiol. The nucleophile for this guy, oh, I hope you did this. Oh, I hope you did this. This is so important. And the nucleophile for this guy is hydride. Oh, I hope you did that. Okay, now considering which carbon they go to, both regioselectivity and stereoselectivity must be considered. Let's look at that. All right, so we have a nucleophile that comes in, which I'm typically drawing as NU, okay? Nucleophile comes in. Is it going to come in here? Boom. Or here? Boom. Option 1 or option 2? Well, the answer is on page 655. I do recommend you go look at that. Page 655. Page 655. I don't even want to tell you. I want you to go look it up. You'll be better off if you do. And of course, the same question goes here. Can you see what the difference is? What is the difference? Say it out loud. Say the word out loud. My wife just sent me a text, and I want to see what this says. Excuse me 1 second here. I can't tell this what this says. Okay, I'm going to come back to that in a little bit. Pardon me. Pardon me. I'm here with you, but my heart is at home with my wife. So I need to come back here though with you. We got to get this done. So, all right, nucleophiles. What's the difference between these two carbons? Say it. My question is too broad, I know, to be a good question, but try. What is it? I know that's not the word you used. Crowdedness. Substitution. Did anybody say primary? Tertiary? Okay, those are all good words to use with this. You see the difference? One's crowded and one's not. Okay? Substitutedness. Okay, those are all good words. Can you see that this one's a primary carbon and this is a tertiary? No, yeah, tertiary carbon. Can you see that? Wow, big difference in its crowdedness. Okay, I gotta go and look at that. I gotta talk to my wife here in just a minute. All right, so for now, let me say, the answer's on page 655. I'm gonna tell you the answer now. The answer is, it goes to the less crowded position. Okay? It goes to the less crowded position. So the nucleophile is going to come here, and the answer for this first one is going to be, let's see, 1, 2, 3, 4. 1, 2, 3, 4. Okay, so it looks like we've got a nucleophile on 4. And a hydroxide on carbon 2, right? It's going to come into the less crowded position, and when it does, this is going to go here. That's not going to happen. That's going to go here, and then we're going to have an alkoxide, and the alkoxide is going to get protonated with the water. All right? So you draw the solution for this one. I think it's also in the book. It's probably also on page 655. All right, so that's a ring opening of epoxides. Now we're going to have a sort of a small variation on that here in just a minute. And this is really cool, really, really cool. So for ring opening of epoxides, it's going to go to the, less crowded position. Okay? Now, if we do this with an acid, we substantially change the reaction. Acidic conditions with a proton, we substantially change it. Why? Because we've changed the leaving group. Can you see this leaving group now? The leaving group before was an alkoxide, which is a horrible leaving group. It does work for epoxides, but it's not good. But if we protonate this guy, aha, now the leaving group is an alcohol. Okay, so it's a very similar mechanism if everything else is equal. If everything's very simple, it's a very similar mechanism. We first of all protonate, make the leaving group, we change the leaving group. I want to emphasize this. We're going to do this a lot. Change the leaving group. We're going to do this semester a lot. Very cool. We've already done it. All right. So, and we're going to do it more. All right. Then the nucleophile comes in, boom, boom, and we're done. Wham. Okay? Very cool. Now, why is this a big deal? Because we can change the stereospecificity of it. All right, so look at this. If we have, a water or an alcohol can be used as a nucleophile under acidic conditions. This is cool. All right, so if we protonate that, we're going to get right? And then my water, I'm going to draw the mechanism out for this one, but you need to pause the video when this is done and write the mechanism out for your for the other one. Goes there, and that goes off to that. If I could force you to do this mechanism, you'd be better off. I wish I could. Right? And if this is acid catalyzed, then we're going to have another water molecule that comes along and takes that proton, and we get boom. Right? Look at that. Wonderful. Okay. Now you do the same thing down here. Pause the video and do the same thing. I'm about to do it, so Okay, hopefully you paused it. Now, first thing's going to happen, where's my marker here? First thing's going to happen is we're going to get, boom. Try to leave myself some room here. Right, change the leaving group. Then we have an ROH. Just going to come here. And that goes there. My bride is texting me. I'm dying to talk to her. I'm stuck here with you. It doesn't sound very nice, does it? Okay. You see what I've got here now? Hopefully you did this while I was... here's another alcohol now in the soup that comes there. Boom. And we get, look at this. R-O... I'm worried about my atoms, okay? Let's go, boom. 1, 2, 3, 4, 5, 6, okay? 1, 2, 3, 4. You see what I'm doing here? I've told you in class that the most common mistake is miscounting. OH. I'm not worried about this OH now. I got the 4, I got the 5, 6. I'll worry about that, you know. But I do now see, aha, okay. I got my lone pair of electrons back over there, and I'm done. That's done. What do I have over here? A protonated alcohol. But this was acid catalyzed, right? I was in acidic conditions in the beginning. So we're done. That's it. So what do you get down here? It's an ether, right? You see the ether here? Granted, it's an alcohol too, right? We got this alcohol up here. But that's what we get by making that, or by using acidic conditions in an alcohol with epoxide ring opening, okay? Now let's talk about the regio specificity and stereoselectivity. Look at this. Propose an explanation for the following regiochemical observations. This is cool. Now the book tells you the mechanism, but you should think about it before you go and look at the book. This is on page 659, by the way. But don't go there yet. Page 659. Think through this. Tell me that with acidic conditions, the nucleophile goes to the less hindered position. Okay? But also in acidic conditions, if it's less hindered, if this is secondary. But if this is tertiary, it's going to go to the more hindered. Why? Why is that? Okay, the answer's on page 659, and here it is. If the nucleophile preferentially attacks the tertiary carbon, this is another good question. Attacks the tertiary carbon under acidic conditions, is the mechanism more likely SN1 or SN2? Think about this. Do not miss out on this opportunity to think about the trends, okay? If the nucleophile attacks the tertiary, is the mechanism more likely SN1 or SN2? Okay, I'm not even going to tell you the answer. I want you to think about that. All right, considering the observations below, is the mechanism SN1 or SN2? Same question, really. SN1 or SN2? Okay, what is the answer to that? Is it more likely SN1 or SN2? And that's a hint for how this happens. Okay, it's addressed on page 659. So let's look at it. When the nucleophile attacks the tertiary center of the epoxide, the intermediate it attacks on some carbocation character, but not completely. So look, if you protonate this oxygen, can you see this is the epoxide here? That's the original epoxide. We protonate it, and we make a better leaving group, okay? If we make a better leaving group, which side is it going to leave? Gosh, this is such a good leaving group, and a tertiary carbocation is so not bad. We've seen that before, right? tertiary carbocation is something you see. That's the whole reason we have SN1 mechanisms, is because tertiary carbocations are okay. They're not bad. So since that's the case, even before we have a nucleophile come in, even before we have it, this hydroxide starts to leave. Well, when it starts to leave, oh, look at that. Oh, think about that. Don't go to sleep now. If you can think about that, it'll settle in your head nicely. When it starts to leave, it makes sort of a trigonal planar substrate. Really? Yes, yes, of course it does. Because that's what happens in an SN1 mechanism, right? Okay, so if it makes an SN1, if it makes a trigonal planar substrate and it makes, you've got a partial positive on there, bam, that's why the nucleophile attacks that. Wham! Look at that. That's got a minus on it. Cool, huh? That's why. Okay. All right. So there's your answer, and I think that's it for this. That's it for that. Now go practice with Skill Builder 14.5, and thank your lucky stars for Klein. A good treatment. Good luck.